get started. Welcome everyone to another talk at Chilloquium, hosted by the Harvard-Radcliffe Society of Physics Students. My name is Andrew Vinitsky. I'm an undergraduate studying physics and mathematics at Harvard, and I'm one of the organizers of our Chilloquium speaker series. I'm here today with my co-moderator, Minchell Park, and we're very honored to have Professor Nima Arkani-Hamed from the Institute for Advanced Studies speak with us today. As always, if you have questions at any time, you can raise your hand in the Zoom participant sidebar and we'll call on you, or you can privately send a message to me and I'll ask for you. If you haven't been with us before, Chilloquium is a speaker series designed to introduce undergraduates to exciting directions in physics. Organized by undergraduates from the Harvard Society of Physics students, our goal is to invite inspiring role model scientists who have made significant contributions to physics and facilitate discussion about their background and their work in a more relaxed fashion than a typical colloquium. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as we can. So we'll generally be prioritizing questions asked in person over privately messaged questions. In the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they are speaking, and also have your video on if you're willing and able. Now Minchell's going to go ahead and introduce our speaker today. So Minchell, take it away.
Thank you, Andrew. To briefly introduce today's speaker, Professor Nima Arkani-Hamed is a renowned high-energy theorist who studies quantum field theory, string theory, cosmology, and collider physics, which are most of the subfields in high-energy theory. Especially, he is well known for suggesting a lot of novel ideas, including amplitude hadron in twistor string theory. Even though understanding his research achievements requires in-depth background in physics, he is preparing an informal talk today for undergraduate audience of Chilloquium. Please welcome Professor Arkani-Hamed with a big round of applause. Thank you.
All right, everyone. It's really wonderful to be here. I'll triple check for the umpteenth time that you can hear me, right? All right, excellent. Very good. Now, I understand that the sort of typical way these things work is some time discussing an interesting frontier topic in research, and then Q&A where we talk about everything under the sun. And I think that's wonderful, and I'm here for as long as you want to talk. And I have no really fixed agenda as well. There's just some sort of basic exciting points about where we are in fundamental physics that I'd like to tell you about. But really feel free to interrupt at any time and slow me down, ask me to explain something in more detail, whatever you want. This is really meant to be more of a conversation. So what I thought I would tell you about today is actually a line of work. Well, it's a sort of very big part. The grand question is a very, very big part of the heart and soul of what fundamental physics is confronting in the 21st century. But it's also been the sort of focal point of my own research over the past sort of 10 years or so. And it's this associated with this sort of rather dramatic slogan of the end of spacetime. And as we might even see as we go through the talk, that it's really something even more dramatic than this, that there are lots of indications that we'll come to see that both spacetime and quantum mechanics have to be seen as somehow derivative, arising from more primitive structures, and that we're just starting to get inklings, little clues here and there about what these deeper, more primitive structures might be about. Now, to begin with, almost all of you know, perhaps all of you know, that the 20th century in fundamental physics started with revolutions, and the revolutions were those of space-time and quantum mechanics. Beginning in the early 1930s, people started trying to put together these two big principles. They started trying to figure out how to talk about laws of nature that were compatible both with the principles of quantum mechanics and the symmetries of Lorentz invariance at the same time. And on the face of it, this is nearly impossible. It's actually sort of easy to understand at least what the basic conflict is. Of course, relativity removed the distinction, didn't erase it, but it blurred the distinction between space and time. We know that we can rotate space into time under Lorentz transformation. So sort of time has less of a very, very privileged role. Certainly the absolute clock of Newtonian physics does not make an appearance in relativity. On the other hand, quantum mechanics, which is much more revolutionary in so many ways, it totally changed what we think physical laws supposed to be about. It changed almost everything, but its notion of time evolution was exactly the same as the Newtonian notion of time evolution. You specify the wave function of a state at time equals 0, and you can evolve into the future if you know what the dynamics are. Let's say you know what the Hamiltonian. So time has the same privileged role in quantum mechanics as it does in Newtonian physics. And so just the kinematical language of space-time and of quantum mechanics are different, and that's why it's non-trivial to put the two sets of principles together. There's a theoretical structure that people started putting forward in the early 1930s that lets you talk about laws of nature that are compatible with quantum mechanics and space-time at the same time. That's the sort of broad framework of quantum field theory. And much of the rest of the 20th century was devoted to understanding better what quantum field theory is about, on the one hand, and on the other hand, finding a very particular quantum field theory, specific instantiation of these general rules that describes all the elementary particles and the interactions in nature that we've seen from distances of around 10 to the minus 17 centimeters. That's 1,000 times smaller than the nucleus of the atom. The distances that are being probed at accelerators like the Large Hadron Collider, all the way out to the cosmological Hubble scale, around 10 billion light years across. And it's incredible that over these sort of roughly 60 orders of magnitude, there's one set of underlying principles of quantum mechanics and space-time in this one particular instantiation of the standard models of particle physics and cosmology that hold sway and describe all the phenomena in principle over this enormous range of scales. Quantum field theory has many, has many general predictions that are very striking. For example, one of the consequences of putting together quantum mechanics and space-time is the presence of antiparticles. Antiparticles are forced on you when you have both quantum mechanics and Lorentz variance. It's highly unobvious fact, but it's true. That's a very general consequence. Another general consequence is the connection between the spins of particles and whether they're bosons or fermions. In quantum mechanics, you could imagine particles are either bosons or fermions, but there's no reason a priori that whether they're bosons or fermions has anything to do with their spin. And yet we've understood that particles that have odd multiples of a half h bar of spin have to be fermions, and even multiples of a half h bar in spin have to be bosons. So that's another general consequence of putting together quantum mechanics and space-time. There's a very specific quantum field theory, the standard model of particle physics, that in detail describes the universe that we see over this enormous range of distance. Okay, so those are the 20th century revolutions. And that puts in even higher relief the real storm clouds of the 21st century that we have very good reasons to believe that at least one, if not both, of these sort of pillars of our understanding of the universe that are so stunningly successful otherwise are likely going to have to go in the next description of physics. So the first argument for this, these are very simple thought experiments. It's one of the beautiful things about this subject is that the big questions are really simple to motivate and explain. So one of the slogans is that because of gravity and quantum mechanics, space-time is doomed. And so let's see what we mean by that. So I'm afraid you're going to have to suffer with really terrible artwork in this talk. There's a good reason I'm a theoretical physicist and not an artist. So this is supposed to be a magnifying glass. I have many apologies, okay? But I'm doing a thought experiment where I'm trying to look at some region of space and time, even some region of the vacuum, just to see what's there. Now, because of the uncertainty principle, in order to probe distances or time for delta t, you need energies of order h bar over delta t. Here working with natural units where h bar and c are set equal to 1. We can have a lot of fun if you want in the Q&A to talk at length about natural units and why it's the best possible way to do physics. So I'd be very happy give an entirely separate talk about the glory of natural unions. But anyway, the amount of energy we need to probe this little region of space goes like 1 over delta T. Now, that's why we need the largest accelerators on the planet, the biggest scientific instruments that humans have ever made to probe the tiniest distances that we've ever probed. That's a very big irony, right? We have these enormous machines, the Large Hadron Collider, probe the tiniest distances that we've ever probed. Why is that? That's a direct reflection of the uncertainty principle, the need to go to ridiculously high energy to probe tiny distances. And in a world without gravity, there's no limit in principle to the small distances that you can probe in this way. But in a world with gravity, something very bad happens. At some point, you put so much energy into such a tiny region of space that effectively the enormous amount of energy in a tiny region of space is like putting an enormous amount of mass there because of E equals mc squared. So an enormous amount of energy in a tiny region of space will eventually collapse the tiny region that you're looking at into a black hole. You're putting more and more energy into a smaller and smaller region of space until you put so much energy in that tiny region, the escape velocity exceeds the speed of light, and you produce a black hole. So that happens if we just extrapolate what we know about the strength of gravity to arbitrarily short distances. That happens at this famous distance, that's the Planck length. It's around 10 to the minus 33 centimeters. The corresponding length scale is around 10 to the minus 43 seconds. Okay, so this is a ridiculously tiny length scale. It's 16 orders of magnitude smaller even than the tiniest distances that we're probing in experiments today. Nonetheless, it's a thought experiment that we can do. And the thought experiment tells us that there's no way that there's no operational way of probing a space and time separations that are smaller than this Planck length. Now, every time this has happened to us before in physics, what we find is some notion we can't even in principle give operational meaning to. It's meant that those notions are approximate. They're not really there in the correct equations of physics. The immediate antecedent to this argument is has to do with the uncertainty principle. Before Heisenberg, we thought we could ask the question: what is the position of that electron and how quickly is it moving? And that's a question that you can say in a natural language like English, but it turns out to be a meaningless question about nature. Okay? So, it ended up being position or momentum rather than position and momentum. And there are similar thought experiments that happened back then that concluded that you couldn't actually determine the position and the velocity at the same time, even in principle. Well, we're in a similar situation today, except the thing which appears to be approximate is even more dramatic. It's space-time itself. Okay, we can't even give, in principle, operational meaning to space and time separation.
Professor Hamed, Professor Arkani.
Yes.
Yeah, I actually have a question of the previous slide and also
Sure.
like some logistic question. So first about the logistic question, I think that many people cannot hear you very clearly. So may I ask whether you have an audio problem on your side? I think
Yeah, that's why I was asking before. Is this any better now or no?
I think we can hear you, but like, oh.
Is it better or not?
This might be
sounds better.
Yeah.
All right. Sometimes when this happens, this just started happening yesterday, and I tried just reconnecting to the Zoom link, and that helped. But I can do that. But if you can hear me a little better now, I can also just try to speak closer. Is that better now?
It's going in and out. I would say, like, it'll be good for a second and then it'll warp.
I see. Well, let me try doing something here. Just 1 second.
Yep.
Just one sec. You might have been free to interpret. You might have interpreted sort of Heisenberg's thought experiments too, as well. There is such a thing as position and velocity. We can just never determine both at the same time. There's some resolution. There's some fuzziness permanently, right? It just turned out that that in that case, the correct interpretation was that there is no sort of fuzzy both space and both position and momentum at the same time, but it was telling us something profound, that in the correct equations, we can't talk about both at the same time. So we don't know that's going to keep happening again and again. It's just that it's happened so far. that every time you come, and that's not the only example, there are a number of other examples of this sort, that every time you come up with some sort of notion that you can't even in principle give operational meaning to, it's a likely clue that that notion is not going to survive in the more complete understanding of physics. So these are a few of the precious clues we have for what the character of the next big developments in physics might look like.
So here, like you,
but it's not a fact. This is just it's a clue. It's a clue that we're interpreting in a particular way, given the way the history of physics has worked in the past.
I see. Thank you so much. Got it.
And you guys can continue to hear me okay? Just check. All right, excellent. Very, very good. All right, great. So now, where are these questions relevant? They're relevant in places like the expanding universe. So if we take the picture of the expanding universe and we extrapolate back in time, there is a sort of famous moment, we often colloquially call the Big Bang, where what's happening is that the curvatures of space and time are of order 10 to the minus 33 centimeters, 10 to the minus 43 seconds, these Planck scales. And again, I'm sure you've all heard this kind of statement, but often people ask what happened before the Big Bang. And it's very likely that even the word before ceases to make sense. Even the very notions of space and time are breaking down in the neighborhood of the Big Bang. So we don't even know what it means to ask what happened before the Big Bang. Something very similar happens when you throw yourself into a black hole. The interior of a black hole is very much like the picture of an expanding universe run in reverse. So it's like a crunching universe. When you go inside of a black hole, you're inevitably drawn towards this moment in your future where you're crunched. And similarly there, what happens near the crunch? We don't know. Professor, these are places where theories just break down when quantum mechanics and gravity both become dominant.
Professor, okay. I think there's a question in the chat. Jackie,
yes,
do you have a question?
Yeah. When you talk about the Big Bang, are you referring to the start of the traditional Big Bang cosmological picture? Because
no, I'm referring to the Big Bang singularity. You're right. There is a kind of a nomenclature point that sometimes people talk about the hot Big Bang as the kind of beginning, at least an era where the universe was dominated by radiation with a little bit of matter, and we have extremely good evidence for the existence of that era. Starting with a time about a second after the conventional Big Bang that I'm talking, the singularity Big Bang that I'm talking about. But we have very good evidence from looking at the synthesis of light elements and so on for this hot early period of the universe. That people, I think that's what they conventionally call the hot Big Bang. Here I'm talking about what you could call the Big Bang singularity, the sort of place where if you run the equations back, there's the t=0 moment. And at t=0, all hell is breaking loose. And we just don't even know what t means anymore. So that's what I was talking about here. Did that answer your question?
Yes. I was wondering if you were referring to the singularity before inflation and.
Yes, that's right. Because the thing is that even if you have inflation, it's kind of a relatively simple fact that even if you have inflation, you cannot avoid the existence of a singularity in the past. Basically, one reason for that is in an expanding universe, everything dilutes. The particles get stretched out, wavelengths get stretched out, energy goes down, energy densities go down, and so on. Inflation is an incredibly good way of diluting. So that's an extremely effective way of diluting. But all the things that it's good at in the forward direction, it's bad at in the backward direction. Okay. So if you have tiny little inhomogeneities and you go back in time, instead of getting red shifted, they get blue shifted. And inevitably, at some point in the past, you'll have infinite energy densities, infinite temperature, infinite something, infinite curvature. And there are theorems along these lines that you can prove that you cannot avoid a singularity in the past, even if you have inflation.
Okay, thank you.
Did that answer your question?
Yeah.
All right, great. All right, excellent. So let's now over the past, there's much more there are deeper and more subtle ways in which this sort of end of space-time manifests itself. I'll mention kind of one of them. Well, I'll mention the sort of main one, which is even more dramatic, although it's less, people in popular books talk about it less. Quantum mechanics change what it means to know something. Quantum mechanics puts a limit on what it means to have a well-defined observable. And because it's a probabilistic theory, in order to talk about anything meaningful, in principle, you have to repeat an experiment infinitely many times, right? After all, we're trying to determine some probability, and the notion of a probability only becomes precise in the limit where you do the experiment infinitely often. If we do the experiment n times, there's an irreducible error associated with that, a statistical error that scales like 1 over the square root of n. And that's a practical thing. That's the origin of statistical error, ultimately, like in particle physics experiments, where colliding the same damn protons, they're exactly the same initial state over and over again at the LHC. Something different happens every time. That's quantum mechanics. And if you do the experiment 1,000,000 times, there is an error of order 1 over square root of 1,000,000, you know, part per 1,000 associated with anything you measure. Okay, so that error in principle can be sent to 0 if you do the experiment infinitely often. So quantum mechanics, in order to talk about observables, needs you to take a limit where you do the experiment over and over again as n goes to infinity. That we teach undergraduates. There's another fact which we emphasize a little bit less, which is that quantum mechanics also asks you to do the experiment with an infinitely large measuring apparatus. And if the apparatus is not infinitely large, then there's another source of inherent uncertainty associated with the quantum fluctuations of the apparatus. This becomes obvious if you take an imaginary limit where your apparatus, instead of being some big thing with like knobs and dials and pointers and so on, if you think about the apparatus being 3 molecules, what the heck would it mean for the apparatus to measure something in that limit? And actually, this error is much less practically important because it scales like e to the minus n, where n is the number of degrees of freedom of your apparatus. But just to push the point, let's say you or me, any of us, we're made of roughly 10 to the 30 atoms. Let's say for some reason we got it into our head that we wanted to measure any quantity. I don't care what you want it to be. Pick it the G minus 2 of the electron, just because it happens to be one of the most best measured numbers there is. Let's say I really wanted to know the G minus 2, not to 12 decimal places like we know it today, but to the, wait for it, 10 to the power of 10 to the 40 decimal places. Okay? Not 10 to the 40, no. 10 to the power of 10 to the 40 decimal places. Well, that's essentially meaningless for you and I to talk about. Why? Because let's say I'm sitting there, I'm going to do the experiment, dum-de-dum-de-dum-de-dum. By the time I get to around the 10 to the 30th decimal place, I could quantum mechanically fluctuate into a cloud of dust. That would certainly put a damper on my measuring the 10 to the 30th decimal point of the G minus 2. Or one of the less bad things that could happen is that I could have a quantum fluctuation in my brain, and instead of writing down 7, as I should, in the 10 to the 30th decimal place, I write down 2. Okay? Any finite system has an irreducible error associated with any measurement that it can make of order e to the minus n, where n is the number of degrees of freedom. Now, it's obvious why this error is utterly practically irrelevant relative to the counting error, the statistical error, which is 1 over square root of n. That's a really big deal, right? But it's there, and it has a very dramatic consequence, which is that if you try to make any measurement in a fixed size room, any measurement at all, but any measurement that the fancy word for it is a local observable. But in practice, it means that anything that you can try to measure over a fixed period of space and time, it's impossible to give arbitrarily accurate meaning to any such observable, because you'd have to do the experiment with the larger and larger measuring apparatus to reduce this e to the minus n error. But if you do it in a fixed size room, the apparatus will inevitably get heavier and heavier. And before it gets infinitely, at some point, even when everything is finite, it'll get so heavy that it will collapse the entire room into a black hole. And then you're in big trouble because you can only do the experiment a finite number of times as well before you get sucked into the black hole singularity, okay? So that means that there's an irreducible error on any experiment that's done in a fixed size room. And it turns out that that error scales like e to the minus the area of the walls of the room divided by g Newton, okay? So g Newton has units of length squared. So it's 10 to the minus 33 centimeters squared. So the e to the minus the area of the wall of your room in units of the Planck scale gives you an in principle limit to any observable that you can sort of talk about in finite regions of space and time. So that shows that the issue with this breakdown of space-time is not just something that's localized on tiny scales. It's not just something like the surface of this table that seems smooth, but when I go down to small scale, I see that it's made out of atoms. There isn't some dumb idea like atoms of space-time out there. It's not like that. There's something more subtle going on that we can't even talk about observables on the interior of space and time when we have quantum mechanics and gravity. The only kind of observables we can talk about are where we can take these measuring apparatus. How can we make them infinitely big? We can make them infinitely big by making them further and further apart from each other. And the kind of experiments we're allowed to talk about involve that. Situations where the space-time has some asymptotia, where you can go off to infinity in some way and make your huge infinitely big measuring apparatuses, have them shoot things into the interior of the space-time that collide into each other and go back out and are measured in some way, okay? So that fact that the main observable, the only observables you can talk about when you have quantum mechanics and gravity sort of live at infinity, that's the very beginning of the idea of holography. And that's something that really the string theorists started telling us about in detail in the late 1990s. And there's an amazing fact that was discovered back then. People are still exploring it intensively. I could give a whole other talk just about this subject. You probably heard some yourself as well. But this ideology that you think about the things you're allowed to talk about precisely, and those things live at infinity, takes its most precise form for a particular kind of space-time that's not our space-time, but has some similarities with it. So physicists love to put worlds in boxes, and the kind of simplest analog of putting the world in a box is anti-de Sitter space. So I won't say anything about we won't need any of this in detail for this talk, but the sort of geometry looks like the inside of a tin can. So literally like the inside of a tin can. Time is the vertical axis here. But the interior of this tin can is warped. It's warped in an interesting way in that, so it's not flat space-time, it's a curved space-time. And it has the interesting property that first, it's sort of the same everywhere, so it's homogeneous. So just like flat space-time, you can't tell where you are, it's sort of the same everywhere. These are also examples of maximally symmetric spaces. So the curvature is the same, it's uniform everywhere, uniform negative curvature, in fact, everywhere. But it has the feature that if you look at a point in the interior, the distance to the wall of the tin can is infinity, but light takes a finite amount of time to bounce off the wall and come back. Okay, so you can think of it in some ways as like being inside an infinite quadratic potential well. So any massive particle sees this well, and so if you shoot it up, it'll go and it'll take a long time and come back down and bounce around, but light can make it out to the boundary and bounce off. So it's the closest we can come to the world inside a box. And in this world, the kind of observable you're allowed to talk about, you can ping the sides of the tin can, you can ping the sides of the tin can, looking for the correlations of what came in versus what came out. But since the experiment starts and ends on the walls of the tin can, you're free to sort of speculate that maybe there's a theory that only lives on the walls of the tin can that actually calculates those correlations. And that's what this basic idea of holography is about. The kind of striking thing is that there's a completely ordinary particle theory, no strings, no gravity, none of that fancy schmancy stuff, a perfectly ordinary particle theory that lives on the walls of the box. But when the interactions between the particles are cranked up so they become very strong, and so you can't keep track of what the individual particles are doing, the kind of collective excitations of this big mess of particles is actually encoded in thinking there is an interior, and the interior has gravity and even strings and extra dimensions and all those fancy stuff that actually comes out of the dynamics of a perfectly ordinary quantum mechanical theory of particles that just live on the boundary. So
Professor?
just like ordinary holograms give us the kind of illusion of three-dimensional depth, but coming out of interesting correlations on a two-dimensional boundary, here it's something more sophisticated. It's quantum mechanical correlations, very strong quantum mechanical correlations on the boundary of the space-time give rise to something that can be interpreted as having gravity and strings and all the rest of it in the interior. All right, so as I said, we're not going to talk about this more, but this is our first kind of baby example that it's actually possible for at least space to emerge, space and gravity and strings and all this fancy stuff to emerge out of more primitive ingredients. In this case, the more primitive ingredients are just ordinary quantum mechanics, but when the interactions between particles are incredibly strong. I think there was a question, so maybe we can pause and ask if there's about that, the question there.
Yeah, I wanted to ask about the maximally symmetric space-time. In an expanding universe, don't we not have maximally symmetric because it's not?
We do. It's a different kind of, exactly. We have a different kind of maximally symmetric space-time. When we talk about conventional expanding universe, like Robertson-Walker expanding universe, we don't have all the symmetries we could possibly have because we still have a distinction between time and space. So it's maximally symmetric in space, let's say, but there's still a distinction between time and space. And that's why we say the universe is expanding, or the curvature is dropping, or the horizon is growing. We'd say it in many different ways. If you want a space-time which is maximally symmetric, where the curvature is the same everywhere, there's three possibilities. The curvature can be zero, and that's flat space-time. And it can be either constant positive or constant negative curvature. Constant negative curvature is anti-de Sitter space. Constant positive curvature is de Sitter space. And if you like, it's what we're going into now in cosmology over the last few billion years, as we've seen that the universe is accelerating. So the accelerating universe, as we go deep into the future and forget about the memory of where we came from, we approximate more and more and more this sort of exact maximally symmetric situation. So those are the three possibilities.
Okay, thank you.
Did that answer your question?
Yeah.
Professor, I also have a question about this. So, like you previously mentioned that the infinity is kind of like required for us to like
yes, very much so. Yes,
remove this kind of like adders and stuff. But yes, as I know, like there is a lot of like effort on trying to do this kind of quantum simulation on the like finite size system for this type of the like cosmological like phenomenon as well. So I just wonder like how the quantum simulation, for example, like quantum simulation with atoms or cold atoms, like how they avoid this type of the like
remember a very important thing here is as I said, and before getting too airy-fairy, there's very practical things involved here. The infinity that's needed is of the thing doing the measuring, not the system being looked at, okay? And you and I, or our measuring devices, are definitely infinite as far as any practical level of error is concerned. The kind of limitations that we're talking about are of order 10 to the minus 10 to the 30. It has nothing to do with the number of degrees of freedom in the system, okay? However, the fact that you see, if I told you that what you measure is inaccurate at the level of 10 to the minus 10 to the 30, you might say, I don't care. But you could also might say, look, if I really cared, which I don't, but if I really do, I can always upload my memory into a bigger computer, right? And I can always take a limit where this approximate thing that I'm talking about eventually asymptotes to the exact thing. What's fascinating is that quantum mechanics and gravity put limitations on that. And so if we want to insist on talking about precisely defined things that are likely elements of a correct sort of mathematical theory of nature, we're not allowed to talk about those things, even if the degree of the error seems really tiny. But you know, the degree of an error of knowing where a baseball is for a baseball player is also tiny from the uncertainty principle, but it doesn't change the fundamental importance of position or velocity instead of position and velocity to our understanding of physics. Okay, so all right, so I probably don't have time to talk about this, but I can just give you one idea of just how this sort of magic works. If someone came and told you that, look, there's some way of talking about this extra direction of space in terms of a theory that only lives on the wall at infinity, the first thing you'd say, and the first thing you should ever do when anyone, be it a professional physicist or anyone else, says something sort of incredible sounding, is be very skeptical and say, what the hell are you talking about? And think about really simple possible counterexamples to what they're saying. And if they know what they're talking about, they'll have an answer to those simple counterexamples. So here's one of them. If someone tells you there's some way of describing everything that's happening in this space that has an extra direction in terms of something that only lives on this wall far away, you would say, okay, what happens if I have two particles that are at exactly the same coordinate in this direction, but at two different coordinates in the extra direction? How can I possibly tell them apart if they're at exactly the same coordinate? And part of this dictionary is that the size in the extra direction is reflected in terms of scale size on the boundary. So the way you would describe like a little particle sitting there at some location in this extra space is in some blob of energy on the boundary. And as you move this guy further away, the blob gets bigger. So the size of the lump in the sort of boundary description is a reflection of where you are, the position in the extra dimension. All right. Now, so all of that is wonderful, and there's a huge amount of work in this area. It will, it's going strong. It'll continue to go strong for another many decades to come. But if we take a peek at the actual universe that we live in, there are big differences between this universe and this toy example of a universe in a tin can. And as I just alluded to the fact that our universe is accelerating, the fact that our universe is accelerating opens up the largest Pandora's box of theoretical conundra and challenges that we have to face. Because it really puts every one of our sort of principles under pressure. And the main reason is that in an accelerating universe, what we're going to see now in the cosmos is what we'll ever see. We're not going to see more. If the universe wasn't accelerating, if the expansion rate, if the doubling rate wasn't the constant, then the doubling rate would slow down. And if we waited longer and longer, we'd see light from more and more distant reaches of the universe. But that's not the case. If the universe is accelerating, there are some objects out there that light from them will never make it to us because the space in between is doubling at a constant rate. So for every amount that the light traverses, there's a doubling that gets in the way of the light ever getting to us. Okay, so everything we see now in cosmology is what we're ever going to see. And crucially, it's finite. What we have access to in our universe is fundamentally finite. And that puts everything into question. So we can't have this artificial division of the world into an infinite apparatus and a finite thing that's being looked at. And so even the prerequisites for quantum mechanics to allow us to talk about meaningful observables is there's a rug that's pulled out from under our feet. There are many other questions, of course, about cosmology. We alluded to one at the beginning, the birth of the universe, the Big Bang. Time comes into existence at that point, very likely. If time didn't exist, what does it even mean to talk about quantum mechanics? What does it mean to talk about physics, period? You know, what physics for centuries has been about describing how phenomenon vary in space as you move through time. So what the heck can it even mean to say that we don't have time? So it's these questions about cosmology, both near the birth of the universe as well as in the very late universe, thrust on us by the accelerating expansion of the universe, that suggests that somehow we need to understand not just the emergence of space that we've understood very beautifully in these toy examples, but also of time. And that it's very likely that together with that, we're going to have to learn about some extension to what we mean by quantum mechanics. Now, I want to emphasize here that I'm not saying something like quantum mechanics is wrong or is modified, or that someone doing an experimental lab somewhere will ever get an answer that differs from what quantum mechanics would predict. I believe that in any situation where quantum mechanics is capable of giving an answer, it will give the correct answer. But there are situations now where we think that we're applying quantum mechanics to the entire universe, where quantum mechanics cries uncle, where the kind of where the prerequisites we need to be able to speak about meaningful quantum mechanical observables are taken away from us. And so we likely need to somehow extend our language or vocabulary or grammar in some radical way in order to learn how to deal with this. All right, so that's the kind of first part of this talk, is to give you an idea of what the drama is before I can move on to a particular angle for attacking these problems that's going to come crashing all the way back down to earth. We're going to talk about some very, very concrete and simple things in the remainder of the talk. But I want to just pause at this point to make this sort of general observation that if there's a deeper structure underlying space-time and quantum mechanics, which I think I've tried to give you some evidence that, or some of the main arguments for why we should expect such a structure, it's clear ahead of time that it has to involve some new physical ideas as well as some new mathematical ideas. I think that's certainly familiar. The kind of magnitude of challenge that we're dealing with is very similar, probably even more dramatic than the transition from classical to quantum. And so certainly in the transition from classical to quantum, everything changed. A sort of kinematic structure changed. We started talking about wave functions and Hilbert spaces, and the degree of abstraction change in a significant way. And I think it stands to reason that something very similar is going to happen now. And in the rest of the talk, I want to give you one particular path towards uncovering what some of these physical and mathematical ideas might be. But this is a good time to sort of pause and ask if there are any general questions. Yes. Yes.
Yeah, I have a question.
Yeah.
So back to your example 2 slides back, when you're mentioning how the extra dimension is encoded by the size. So first of all, like, is this quote unquote size like the correlation length of the particle? Like, what exactly is the physical?
No, it's not a particle anymore. What you think of as a particle in the bulk is a blob of energy on the boundaries, okay? And moving that blob, moving a particle in the interior corresponds to changing the size of this blob. Now, there has to be something very interesting about the way these blobs interact with each other, because, for example, if you take two of these, if you take the purple and the green and you shoot them past each other, they miss in the interior, right? But how is it that they're somehow missing when they're just on top of each other? Well, somehow it has to do with the fact that physics on very different scales doesn't find it easy to affect each other. So something on a very large scale, this big green blob would be now in the ordinary direction going this way, with a very much smaller thing sort of piercing and going through it. And they don't affect each other very much. So that's the kind of a feature that we're broadly used to in physics, that physics on very different length scales don't affect each other in a detailed way.
Can I ask, like, how do you distinguish? Let's say, like, in the bulk, you have a particle that's close to the boundary, such that, but it's pretty big in terms of, like, if you go to the boundary description of it, it has a pretty big the size of the lump. And how do you distinguish that from, like, a particle that has a small size of lump but farther away in this extra dimension?
Yeah, so that it would be the sort of character. It's not just they're not simply captured by the fact that they're a blob of energy, but there's very particular patterns of quantum mechanical correlations that you would have between these guys. So there's something highly quantum mechanical about these blobs. That's part of the answer to your question. But yeah, this was just meant to be the beginning of the dictionary. There's a very detailed dictionary that tells you that any kind of how to interpret any pattern of correlations that you can in principle detect from the boundary. So, you know, what you could do, for example, is shoot some particles in from the boundary so they produce a purple blob, and then send light out to say, I made a purple blob, and you detect that back on the boundary. So that's the ultimate experiment, which start and end, that you produce the blob and you detect that you produced it. The result of those correlations that you can measure in principle from infinity are entirely the result of these highly quantum mechanical interactions between the particles purely on the boundary.
So the size is basically like the entanglement length scale when you use the boundary description?
It's related to the entanglement length scale. The sort of the questions about entanglement have to do with the kind of surfaces that would drop into the bulk anchored on these regions. But that would start getting us into more detailed discussion. Here, just the most zeroth order thing is that the reason it's not completely crazy is that position in the extra dimension is scale on the boundary. And one thing I should have said is that you might expect something like translational invariance in the extra dimension, and translational invariance in the extra dimension turns into scale invariance on the boundary. And so that's why, at least for the zeroth order correspondence of this sort, it's really scale invariant theories on the boundary that have a chance of encoding this something with the extra space. And it turns out when you have relativity and scale invariance, inevitably you have more symmetries than just that. You have the famous conformal symmetry. So that's why the kind of basic correspondences with conformal field theories, conformal theories that live on this boundary.
Okay, thank you. Thank you, Scott.
All right, any other questions? All right, well, I see that I've gone on for quite some time, but let me see if I can, maybe can I go on for another 20 minutes or so?
Sure, yeah, you can go on for as long as you want.
All right, okay, very good. Well, I mean, I guess people can feel free to decouple whenever they want. All right, so now I'm going to move on to the things that I've actually been thinking about. My friends and I have been thinking about for the past 10 years or so. And part of the motivation here is, you see, you might be a little discouraged thinking about these questions, that the relevant physics shows up at the Planck scale. And we're not going to do experiments up there anytime soon. And okay, maybe we can think about toy models and so on and have a lot of fun, but physics is an experimental science. We want to describe the things that we see in the world around us. And you might even be wary of spending too much time on toy models because nature's imagination for how to think about physics is vastly bigger than our own. And it would be a very good idea to follow what nature tells you to do rather than what you and your friends decide is cool to think about. And I'm very, very sympathetic with that. That's why I've taken inspiration here from a kind of striking fact I find about the really huge conceptual leaps that we've been forced to make in physics before, which is that when similarly huge conceptual leaps were needed in the past, there were actually clues to those leaps hiding in plain sight as funny features of the existing theoretical framework. And I'll give you one example. It's sort of my favorite example. I like to imagine that you're a classical physicist happily sleeping in your bed in the year 1850 on Christmas Eve, and you're visited by the ghost of theoretical physicist future, okay, in the middle of the night, who wakes you up and tells you, I have news for you from the year 1930. Newtonian determinism is gone. And they vanish into the night, as ghosts of theorists future are wont to do. So what do you do with this information? I mean, you're like, what the hell? How can it possibly be that determinism is gone? It's the most important feature of the Newtonian clockwork universe, right? It's the single most profound feature of the laws of physics that we know work right under our feet. So how can it be that they're gone? That doesn't make any sense. It's crazy. But if you believe the ghosts and you want to do something about it, well, it's very unlikely that in one shot you're going to discover the laws of quantum mechanics, right? That seems completely impossible that you would jump from that information to discovering wave functions and Hilbert spaces and all the rest of it. You could try to do something dumb, which is to add like stochastic terms to the right-hand side of Newton's laws and say, aha, there, I'm going to add some randomness to Newton's laws. And that's also not the right answer, okay? But what you could do is say, gosh, this is such a big hint that if it's really true, the fact that there's no determinism is such a big deal that even the determinism that I see apparently under my feet today must somehow be an illusion. And there must be some new way of talking about even classical physics that doesn't have determinism in it. You can't sort of smoothly deform Newton's laws into quantum mechanics, precisely because of this big deal thing that determinism is hardwired into Newton's laws. But you can wonder, is there some way of thinking about Newtonian physics in a different way, where determinism isn't the star of the show somehow, but it comes out at the end. But this other starting point will be better suited to the generalization which is coming. Okay. Now, is there such a way of thinking about classical mechanics? There sure is, and it's the principle of least action. And when we all learn the principle of least action, I think we're all struck by the same fact that it looks like it's not deterministic. It looks like the particle is sniffing out every possible path that it could take from A to B and choosing the one that minimizes or extremizes the action, right? It sounds really weird. And in fact, the people who discovered it, Euler and Lagrange and de Maupertuis, they were kind of mystified by this fact that it seems so philosophically counter to the standard deterministic Newtonian worldview. Theorists like Dirac and Feynman and others have emphasized a lot this sort of miraculous feature of the laws of nature, that not only are they mathematical, which is pretty amazing already, but that at any given moment in time, they seem to be able to be cast in radically different clothes. They seem to be able to come from radically different starting points. And we don't know why that is, but somehow it's that the first way you run into it may not be the kind of rotation of the ideas from a starting point that's best suited to the next leap, okay? The principle of least action is best suited to the next leap because, after all, determinism isn't there. In fact, it's a little mysterious the other way. It's a little mysterious that despite the fact that it doesn't look deterministic, it ends up being so, okay? And there's a deformation of the principle of least action to sort of Feynman's picture of the summing over all paths. So that's happened to us before, and there are a number of other examples of this sort. And at least in this analogy, we're in a similar place today. If space-time and maybe even the rules of quantum mechanics have to go in the next description of physics, then one thing that we can try to do is think about the physics under our feet today. No speculation, nothing new, just the physics under our feet today, but in a way that space-time and quantum mechanics aren't the stars of the show, and other ideas are the stars of the show instead. Okay, so that's our sort of moving spirit in the next 20 minutes that follows. All right. Now, the last 45 minutes have been a lot of airy-fairy stuff. And so I want to really come crashing back down to very practical things. And I think that's one of the exciting facts about the set of ideas I'm going to tell you about, is the confluence of these sort of philosophical ideas almost about the motivation to eviscerate space-time and quantum mechanics from our description of fundamental physics, and the direct indications from very practical calculations that something like this is needed on the other hand. So let's come and talk about physics at the LHC. You all know probably that the Large Hadron Collider collides protons together around this 27-kilometer ring outside Geneva at energies around 10,000 times the rest mass energy of each proton. And a crucial thing that you have to learn how to do, the protons are messy bags. They're not elementary particles. They're messy bags that are made out of quarks and gluons. And the collision rates are enormous. There's billions of collisions a second. And maybe if we're lucky, we're looking for something new that'll happen beyond the standard model that might happen once a second or once a minute or once an hour. So you have to be able to understand the ordinary collisions extremely precisely to subtract them as a background and look for a signal. Okay, so clearly you have to know how to do that. And remember, the collisions that we care about are these sort of head-on collisions between the elementary particles inside the proton, the quarks and the gluons inside the proton. So one of the dominant things that happens, this happens, hundreds of thousands of times a second. There's 2 gluons come in, 2 gluons come out, 3 gluons come out, 4 gluons come out. They don't come out as gluons. They end up being dressed as sort of jets of strongly interacting particles. But the basic underlying process is that 2 gluons in and a few gluons out. Okay, so you need to understand those to extreme precision to be able to predict what happens. All right. Now, this is not new physics. There's nothing fancy, no black holes, no Big Bang, no strings, nothing like that. It's just completely ordinary physics under our feet. In fact, it's so ordinary that it seems boring. Okay. And so it sounds like an engineering problem. No offense to engineers. Someone has got to actually just do these calculations, and it's not new physics, it's just old physics, right? And in fact, we know exactly how to predict the rates for all these collisions. We have the theory of the strong interactions that tell us that gluons interact with each other in simple ways. We draw these sort of stick figure pictures of processes that take place in space-time. There are Feynman diagrams. That's what made Feynman famous, is that he managed to tell us how to think about these collisions between elementary particles in a way that made the locality of the interactions in space-time and the principles of quantum mechanics sort of manifest at the same time. Okay, so we're supposed to draw all these, so these are 2 in and 4 out. And I'm just drawing the combinatorially all the different ways that you can draw it to make this happen. Every one of these pictures is associated with some rules, okay, with some particular mathematical expression. But the basic idea is that each one of these things is a space-time process, and you have to add all the ways up to get the final answer. So, okay, so if we do this for the practical calculation of 2 in and 4 out, okay, you just get a combinatorial explosion. There's like 220 diagrams, tens of thousands of terms. Here's what it looks like. Actually, if you do 2 to 3, even not 2 to 4, it's about 100 pages of algebra that looks like that. You just do it by brute force. Okay. In fact, 2 scattering is something that we put on graduate problem sets, and we would never torture people with 2 to 3 or 2 to 4 scattering. It's just insane. Okay. And in fact, people needed to. So on the other hand, it's totally straightforward. So you might think not every question is guaranteed to have a simple answer, right? And part of the chauvinism of fundamental physics is a declaration that we only care about questions that have simple answers. So you think, okay, this is just some kind of engineering problem. There's some poor schmoes who have to go actually do the calculation. Unfortunately, the experimentalists really needed the answer to this calculation. Already 30 years ago, they really needed it. And some poor schmo theorists really had to sit down and do the calculation. And the theorists who did this, many people did it, but the people who made the breakthrough were Steve Park and Tom Taylor at Fermilab. And they wrote first one paper with a major breakthrough where they had all the great, they used all the tricks of the day to reduce the 100 pages down to 8 pages. It was a huge advance. And they wrote in that paper that they hoped to simplify the expression a little bit more. And in their next paper, they realized that the 100 pages for the particular case of 2 gluons to 4 gluons was actually a single term. Okay. Now, I'm not explaining what these symbols mean. So these little brackets roughly mean are standing for the square root of the energies and momenta of the particles. I will explain what these minus pluses are. The gluons are particles of spin 1, just like photons are particles of spin 1, but they only have helicity. So photons have polarization, 2 polarizations. They can spin clockwise or counterclockwise, but spin in the direction of motion or opposite to the direction of motion. The same thing is true for gluons. And so the plus or the minus represents whether it's plus helicity or minus helicity. And it turns out that when the helicities are of a particular type, these expressions are just astonishingly simple. So for example, if all the helicities are plus, the expression is 0. If all the helicities but 1 are plus, the expression is 0. And if 2 are minus and the rest are plus, it collapses to this 1-term expression. Okay. Now, back then, it was not universally recognized as the tip of a giant iceberg. That's because it took some time to see that similar simplicity was there everywhere. Okay. But today we know it's a tip of an enormous iceberg, and that Feynman's way of doing the physics, and remember, the reason it's justifiably famous is that it makes the usual rules of space-time quantum mechanics manifest in your face as can be, but making those principles manifest is clearly hiding something else. Okay, you can make space-time quantum mechanics manifest, and you can completely hide that the answer is 1 term. Okay, there's clearly some kind of extraordinary new structure that would immediately give you that 1 term, but presumably there's no free lunch. In that new structure, it'll be less obviously related to space-time and quantum mechanics, right? But you see, now we have a more concrete opportunity that we can try to understand where these amazingly simple things come from. And if we do, then we can try to sort of reverse engineer and see what structures gave rise to these incredibly simple formulas. And if we can discover those things, maybe we can get a clue for where space-time and quantum mechanics comes from. All right, so, okay, so there's another question here. So go ahead, yes.
Oh yeah, thank you so much. This is really exciting. I just want to ask, like, so in case of the quantum mechanics, kind of like the feature of the existing principle was the principle of least action. So for this case, is it the like helicity conservation is the kind of the like hidden like piece?
No, we don't know. There's nothing that's what we're going to be seeing. It's not none of these structures have a simple explanation in terms of any of the obvious things that we know, any of the symmetries or conservation laws or anything like that. So really, much of what I'm going to tell you about next is just what we've been discovering over the past decade, that there are structures underlying these things, that there is a world of ideas that gives rise to this to these things. But that world of ideas involves quite alien, very, very simple, but ultimately rather alien-seeming ideas from related to very interesting branches of mathematics, from combinatorics and number theory, parts of mathematics that have never had anything to do with physics before, but seem to be related in some very structural, basic way to sort of basic physics, not kind of weird esoteric physics, but the sort of physics of the world we see outside our window. And so that's really what I want to tell you about. So this past decade has seen the emergence of new mathematical structures. They're often new to the mathematicians, although in many cases they turn out to be closely related to areas that mathematicians were stomping around in roughly simultaneously. It's very eerie. But it's new mathematical structures in combinatorics, number theory, and algebraic geometry that in really concrete examples can be seen to give rise to these rules of space-time and quantum mechanics. Okay? And so I believe that what we'll be seeing, we're going to be seeing more and more of this in the years to come. But I think what we're looking for is something, is the sort of more radical next step after what we've seen here already. We've seen lots of fantastic evidence that space can emerge from quantum mechanics, from the strong dynamics of quantum mechanical systems, highly quantum mechanical systems. But I think the sort of next step is that we have something kind of, we don't know what it is, some question mark structure, but that quantum mechanics and space-time will emerge from this. And they'll be emerged in a way that are sort of joined together inexorably. And that's what we've been seeing in the concrete examples that I'll show you some pictures. So if I can kind of say what the aim of this program is in yet another way, in physics, we're used to kind of asking questions and looking for an algorithm to get the answer. Okay, so and you can think of the sort of laws of nature as some algorithm to get the answer to questions about what happens if you set up a particular experimental process. But in what we do when we collide particles, like our experimental friends at the LHC do, you collide some particles in, some particles come out, and all you do is measure this in and out at infinity, right? The patterns of in and out at infinity. That's all you see. It's the theorist who comes along and tells you that sort of what's going inside this black box is the particles propagate inside space-time, they bang into each other in this way, that way, you add up all the ways that it could happen. And it's the theorist who makes up that story for what happened. You as an experimentalist, you're not following the proton in to see all the gluons hitting each other one after the other and so on. You're not doing any of that. It's a theorist who's telling that story for what happened in the interior in order to give a rational accounting for the patterns that you see. And so the goal of this program is, in a sense, the reverse of the conventional one. We want to find a different question to which these scattering processes are the answer. And again, I should have said that the observable that we're talking about is the scattering amplitude, right? So again, it's quantum mechanics. So given an initial and final state, there's a scattering amplitude that takes us from the in to the out state. The conventional way of computing the scattering amplitude is to sum over all these processes in space-time in every way they could happen, but we want to find a different question to which the amplitudes are the answer. And that question should not involve space-time, it should not involve quantum mechanics, but somehow it should only take as input the kind of position, the momentum, the velocities of the incoming and the outgoing particles. and see that what the something else is that that gives us the answer to these questions, and at the same time gives rise to the properties of the amplitudes that we normally ascribe to the presence of space-time and quantum mechanics. And so let me give you some more detailed picture, at least for why there's a very concrete strategy here. Part of the point is associated with this slogan, on shell versus off shell. See, ordinarily, when we talk about a particle, it has maybe some form momentum, so it has some energy and some momentum. But these aren't independent. If I take the form momentum squared, it's E squared minus P squared, and that combination is equal to M squared. Okay, so we don't have 4 numbers associated with the particle, we just have 3. The energy is determined in terms of the momentum. So this is often called the on the mass shell or on shell constraint. Okay, but when we draw these pictures, even in sort of popular books, we say, well, these things in the middle are virtual particles. They're not real propagators. They're not real particles. They're virtual particles. And one of the reasons that they're virtual is that obviously, if momentum P1 and P2 are on the mass shell, then unless you make some special arrangement, P1 plus P2 or P1 minus P2 in this example would be that green momentum, will not be on the mass shell. And that's actually very important because in the Feynman rules, even if you don't know about them in detail, there's a factor that looks like exactly 1 over how far away you are from the mass shell, 1 over this P squared minus M squared. Okay, so it's very important that these virtual particles are virtual. They're not real. Otherwise, all the amplitudes would be infinity all the time. Okay, so but it's exactly those virtual particles that are somehow responsible for the explosion in complexity in the apparent answer. So our physical idea is we want to get rid of the notion of virtual particle. Okay, we don't want to talk about virtual particles. But on the other hand, how the heck are we going to sort of determine what the amplitudes are without these pictures? We need some constraints that somehow encode what we would ordinarily think of as the presence of virtual particles from the standard way of thinking about things. And well, here's one of them. Imagine I have this process with particles 1 and 2 in and 3 and 4 out, and imagine that in the conventional picture, what we would say is that we have some virtual particle there being exchanged. Well, one sort of fingerprint, presence, a clue of the presence of this virtual particle is that this amplitude actually blows up. It has a resonance when P1 plus P2 squared is equal to M squared. Okay, so that's very familiar, that when you're exactly on resonance, the amplitude even in classical physics blows up. And similarly here, the quantum mechanical amplitude actually blows up as a pole, 1 over P1 plus P2 squared minus M squared. Okay, so, and those are the only poles that the amplitude has. It doesn't have more complicated poles. It doesn't have a pole that looks like 1 over P squared Q squared minus R squared T squared. The only poles that it has corresponds to what we normally think of virtual particles becoming real. And so the only poles correspond to the sort of long distance propagation of a particle that was virtual a minute ago until you tuned it to become real. Okay, so where the poles are is a statement that reflects the sort of locality of the interactions in space-time. But quantum mechanics tells us more. Quantum mechanics tells us what happens in the neighborhood of this pole, because in the neighborhood of this pole, we have to be able to interpret the amplitude as 2 things happening one after the other. I produce the intermediate particle that propagates a long distance and then it decays. The propagates over the long distance is this blue, 1 over P squared minus M squared factor. But the kind of residue on that pole has to be actually the product of simpler amplitudes, where you produce the intermediate guy and the intermediate guy decays. That's quantum mechanics. That's technically the unitarity of the scattering matrix is reflected in this very direct way in what happens in the neighborhood of this pole. So locality is reflected in where the poles are, and unitarity is reflected in what happens in the neighborhood of the poles as the amplitude splits, factorizes into the product of lower amplitudes. And so we begin to see the kind of a concrete strategy for how to proceed. The rules of space-time and quantum mechanics are reflected in the amplitudes in a very simple way. Locality is the statement the only poles occur when the sum of the subset of the momenta go on shell. And unitarity tells us that in the neighborhood of that pole, the amplitude has to factorize into the product of simpler pieces, of simpler amplitudes. Okay, so this is a constraint. This is how the principles of space-time and quantum mechanics are actually reflected in the answer. Of course, the usual pictures of Feynman diagrams hardwire these facts in, completely made manifest. That's in a sense, their point is to hardwire these facts in. But now we have a concrete strategy. We want to find a different question that's sort of directly posed in the space of these on-shell momenta. We never want to talk about virtual particles. We never want to talk about Hilbert space. We never want to talk about unitarity or locality or any of those things. We want to find a different question that lives directly in this kinematical space, which doesn't refer to space-time and quantum mechanics, but nonetheless gives us all the correct poles and the correct pattern of factorization on the poles. Okay, so that's a more concrete kind of a strategy that gives some more meat to the kind of seemingly airy-fairy idea of replacing space-time and quantum mechanics with something else. Here it's a very concrete question. We want to find some new structure, some new question that has the amplitudes as the answer, which gives us the poles in the right place and gives us the fact of the amplitudes factors. And the picture that's been emerging over this past decade is that in the space of just the sort of kinematical data that labels the scattering process, there is a series of interesting mathematical structures, ultimately fundamentally combinatorial, but associated with some geometric ideas, some analytic ideas, some an interlaced set of fascinating new mathematical structures. The sort of words for them are associated with things like the amplitahedron or associahedra, generalized associahedra, analogs of these things in cosmology called cosmological polytopes. And there are examples of this sort of thing happening. I'm just going to give you, just in 10 minutes, a tour of a couple of them. But what I find beautiful about these ideas is that it really does describe the real world in a reasonable approximation. I mean, the world out there, when we look out the window, not toy worlds that we invent as theorists because we like them. And it exposes some hidden symmetries and new mathematical structures. It's kind of pure magic right under our noses. All right, so I want to give you a sort of a first invitation to give you some hint that there's something going on. So just so there's something you can go play with yourself. So let's look at the very, very kind of simplest theory that we could imagine. The particles would have spin. So they're just the simplest theory of just scalars. So these are things like Higgs particles, for example. And I'm even going to make things simpler to imagine that the labels for the particles go in a cyclic order. Okay, so 1, 2, 3, 4, they go in a cyclic order. And all the diagrams that I'll draw are planar. So no crossing lines. Okay, there's various standard physics motivations for this, but just take this as a rule. So for instance, if I had 2 to 2 scattering, I could have these 2 pictures. Those are the only 2 sort of trees that I could draw with no crossing lines. And I'm only going to be drawing pictures at the moment that look like these trees. Okay, or if I have a total of 6 particles, I could draw this picture, that picture. You could count the sort of 12 other pictures that I could draw, which just look like cubic trees. Okay, so the basic vertex here is a cubic, is a 3-pronged vertex, and I put them together to build tree diagrams. Okay, so following the conventional Feynman rules, the one that I would associate for this diagram would be 1 over P1 plus P2 squared minus M squared. By momentum conservation, P1 plus P2 plus P3 plus P4 is 0. So I could also write that as 1 over P3 plus P4 squared minus M squared. This one would be 1 over P2 plus P3 squared minus M squared, and so on. Now, something that you can tell, if we just look at all the kind of momenta that can occur in these intermediate lines, is that they involve a sum of the subset of the momenta that are consecutive. Like here I had P1 plus P2, here I had P2 plus P3. Here, for this propagator, I could have P1 plus P2. For the next one would be P1 plus P2 plus P3, and so on. Okay, so all I ever see are consecutive sums of momenta. So I'm going to call these consecutive sums xij that go from pi to pj minus 1. And they have a very nice interpretation. Because the momenta all add up to 0, these are 4 momenta, they all add up to 0. Imagine drawing them on a sheet of paper, on a 4-dimensional, or if you're in d space-time dimensions, a d-dimensional sheet of paper. Well, they're going to give you a closed polygon. If you draw one momentum after the other, p1, p2, p3, p4, they're all going to add up to 0, so they're going to give you a closed polygon. And so it's reasonable to look at the distance squared between any 2 vertices of this closed polygon. The distance squared between the I and the j vertex is exactly the sum of these consecutive momenta. pi plus 1 plus dot dot plus pj minus 1 squared. It's a very simple exercise that you can convince yourself that if you just count all the possible dot products that you can have, all the Lorentz invariants that I can make out of these momenta, they're not all independent because they have momentum conservation. So the sum of all the pi's is got equals 0. But the number of these independent dot products is actually exactly equal to the number of these xij. It's exactly equal to the number of chords of this polygon. Okay, so not the edges. Remember, the edges would be just like p1 squared or p2 squared, p3 squared. Those are just the masses of the particles. But all the other chords of this n-gon represent possible propagators, and it's also a basis for all the possible dot products or linear combinations of dot products that you can build. All right, so now. Let's say, though, that we didn't know that this is what was going on. We're an experimentalist who was just, twiddling the dials. They are allowed to move things around that changes the value of these xij's. What would a lazier experimentalist, or this is the hero of my story, also a smart experimentalist, do? They wouldn't do any detailed measurements. But they would get excited by the fact that the amplitude blows up somewhere. So they would notice, for example, if for the case of 4 particles, if the amplitude blows up when p1 plus p2 squared is equal to m squared, or p2 plus p3 squared equals m squared, but not both. Even though those are sort of 2 independent variables, that by the time they make p1 plus p2 squared blow up, they can't do anything else to make anything blow up more. Now, that to us, in the conventional picture, that's because there's no space-time process that we can draw that both has a kind of an internal line for p1 plus p2 and p2 plus p3. These are different diagrams. Okay, but this person doesn't know that. They just notice a pattern that the amplitude blows up when p1 plus p2 squared is m squared, or p2 plus p3 squared is m squared, but not both. When they go to the next case of 5-point scattering, they notice something a little more interesting. There's a pattern to how the blow-ups can happen. Now, if you, let's say, put p1 plus p2 squared to m squared, then if you move the other variables around, you can make it blow up a second time. You can make it blow up also when p1 plus p2 plus p3 squared goes to m squared, but not when p2 plus p3 plus p4 squared goes to m squared. And this is also similarly back in this picture, because I can have a picture where I have p1 plus p2 and then p1 plus p2 plus p3, but not where I have p1 plus p2 and p2 plus p3 plus p4. There is no local space-time picture that has the other guy. Now, we can say this in the language of these n-gons that I talked about before. It has a very, very sort of a pretty interpretation. So let's look at what was allowed here. What was allowed here is p1 plus p2 squared, which is that line, and p2 plus p3 squared, which is that line. And they're not allowed at the same time. And you can see they're not allowed because those lines cross each other. On the other hand, if I go to this 5-point example, I can have p1 plus p2 squared, that's that one, and also p1 plus p2 plus p3 squared, which is this purple one. This is allowed because they don't cross each other. But if they do cross each other, it's forbidden. There is no local space-time process that has them. So now we're sort of translating the pattern of poles, the pattern of how the amplitude can blow up, one at a time. Then once you make it blow up, you want to make it blow up more. It has to do with whether the chords that you draw in these pictures cross or not. Okay. And let me just stress again that these are our 2 big principles of locality, space-time, and quantum mechanics, locality and unitarity. Locality tells us that the only pattern of poles that come together have to correspond to non-crossing chords. So the crossing chords are not allowed. Unitarity tells us what happens in the neighborhood. In the neighborhood of one of these poles, let's say when this xij goes to 0, what should the amplitude do? Well, remember, we should have factorization. It should factor into the product of two smaller amplitudes. And what is it going to factor into? Well, it's sort of obvious from the picture. We just cut the n-gon along that chord, and it's the product of the sort of little left amplitude and the little right amplitude that I get by cutting along that chord. Okay, so now we're starting to define our question a little bit more precisely. We want to understand, well, is there some sort of fact here about locality and unitarity? Is there some fact about these patterns that we didn't know before? And there is. And it's that the pattern of the poles actually has a shape. So in other words, if the experimentalists wanted to kind of present these rules, if they wanted to present how can the poles come together, they could present them in the following, they could notice they could present them in the following kind of striking way. So, so you could imagine that we have this case where I have the amplitude and I have a pole corresponding to this chord. Okay. All right. And I'm going to denote that by just drawing an edge. This next edge over is a different chord, and the vertex that they share is both chords that are allowed at the same time. All right. So you see what I've managed to do here is draw a picture where the edges correspond to a single chord and the vertices correspond to a pair of chords which are non-crossing. Okay. Now, this case looks a little bit simple. It's totally coincidental that it's also that it's 5 points and it's a pentagon. We'll see a more interesting example in a second. But what I want you to see from here is that it's possible to kind of record in a shape the pattern in which all these poles can come together. Okay, and you can think of the interior as just being no chords at all. The codimension 1 boundaries, the edges are 1 chord. The codimension 2 boundaries, the vertices are 2 chords that are all compatible. They're all non-crossing in this way. So that's the picture that I would have for 5 points, and the picture I'd have for 4 points. Is there just 2 ways that I can draw the picture? The interior is just the square. One edge is this sort of triangulation. The other edge is that simple triangulation of the square. All right. Now, now let's say the experimentalist is ambitious and wants to present a similar picture, if one is possible, for 6 points. Well, it's not even possible you can do it. If you can draw a picture, it would have to be 3-dimensional, because I can have up to sort of 3 poles come together. But how do you know if you can do it? It's not obvious that you can do it, but if you knew a little bit of math from the 1700s, you would tell the experimentalist, well, can you just count and tell me how many single poles are there? That count to say, oh yeah, there's 9 single poles. You say, okay, how many double poles are there? You say, yeah, there's 21 double poles. And how many triple poles are there? Well, there's 14 triple poles. Okay, well, then you say, well, is it possible that there's a shape that the single poles would have to be faces, the double poles would have to be edges, and the triple poles would have to be vertices? So is it possible if there's a shape with 9 faces, 21 edges, and 14 vertices? Well, if it's possible, you know, the Euler sum has to add up to do. V minus E plus F should equal 2. And indeed, 9 minus 14 plus 21, 9 minus 21 plus 14 is equal to 2. So it has a chance. And amazingly, there is a shape which does that. Okay, this is the shape. It's called the issosahedron. And it was first discovered by mathematicians in the 1960s. In this picture, I've only drawn explicitly all of the vertices. So you see, it's this kind of cool-looking shape. Every vertex is a complete triangulation of the 6-gon. Okay, every vertex corresponds to a triple pole. Every facet, you see, it has 6 faces that look like pentagons and 3 that look like squares. And I've drawn just a representative one, and you can have fun filling in the rest of this picture. I've drawn one of them is this guy, which would correspond to this single pole. The edges have to correspond to 2 poles or 2 chords. And again, the point is that when faces meet, everything is compatible. Okay, so this edge, for example, this edge is the meeting of this face and that face, where the two chords of this edge are the chords that we see on the corresponding faces. And if I filled in the rest of the picture, then you could tell me what then when they meet at a vertex, it's all the chords from each face are compatible. Okay, so this is not at all obvious that it's possible, and it's true for any n-gon. That for any n-gon, there is a shape, there's a polytope that lives in n-3 dimensions. All the vertices are complete triangulations. All the facets are just partial triangulations, and two facets that meet on a lower dimension facet just give you a more refined triangulation that's compatible with the two coarser triangulations of each facet. Okay, so this is a remarkable fact. That's a fact about the sort of pattern in which the poles can come together, this fact is not the one that we sort of normally talk about. What we talk about is the locality and the unitarity. But in fact, this picture also knows about locality and unitarity. It's really cool. This picture also knows about locality and the unitarity because this icosahedron, these shapes have the following remarkable feature, that if you go to their boundary, the facets on the boundary are actually direct products of lower icosahedron. So for instance, if I go to these pentagonal boundaries, this is like taking the 6-point process and having 5 on one side and 3 on the other. And so it's like that kind of factorization, or like taking the 6-point, and that's exactly what we'd expect, because remember, the shape for the 5-point guy was a pentagon, and I didn't even bother telling you what the shape was for the 3-point guy. There aren't any poles at all, so it's a point. So, and there are 5 of these pentagonal faces, and that 5 is exactly what you'd expect with this factorization. With 5 on one side and 3 on the other side. There are 3 of these faces that look like squares, and they correspond to the factorizations with 4 particles on one side and 4 on the other side. And remember, the shape for the 4-particle guy was an interval. And what is a direct product of an interval with another interval? It's a square. Okay, so that's what these 3 square shapes look like. So these shapes not only have the property that they capture the sort of combinatorics of the triangulations of the n-gon, which are the same as the combinatorics of how the poles come together. They also know about factorization because they have this remarkable property that on the facet they factorize into the direct product of lower objects of exactly the same type. Okay, so the kind of physics of unitarity and of locality and unitarity is what's starred in the kind of Feynman diagram picture for what's going on. In a different way, it's also the star of the way that the string theory talked about scattering amplitudes. I won't explain anything about that, but that fact, the sort of particle in the string picture, are all about locality and factorization. However, they don't make it obvious this kind of more primitive fact about the pattern in which all the poles come together. But as I've said, it's asymmetrical because this picture actually does know about it. This picture not only knows that all the poles come together in this shape, but it also knows about locality and unitarity. Okay, so this is just one example of the kind of structure which is out there, and kind of a hint that there's a sort of a combinatorial structure out there in this simple kinematic space, which knows something about the physics of locality and unitarity from a larger object. Okay, and it also gives you a hint in this example of how the locality and the unitarity, the space-time and the quantum mechanics, are not far from each other. They're all the same thing. It's all features of the geometry of this object and the sort of recursive property that they have, that when you go to their facets, the way they decompose into simpler objects of the same type. Okay, so that was the invitation. I think I've gone on really a long time, so I won't give you a second example. Maybe we could stop now if people want to see another quick example. I can do another quick example. But I hope that gives you a sense, at least for some of the more concrete questions that start arising in this way of thinking about it. All right, thanks a lot.
Thank you so much, Professor. That was a really wonderful talk. It looks like we have a question from the audience. You can go ahead and ask that.
Hi. I don't know if I followed everything that you said at the end, but does going to like order n and perturbation theory correspond to like an associahedron in some way, or are you mixing the different orders?
We're only looking at tree amplitudes, and then there's a generalization for the most general case. That's actually really what we've been doing over the course of the pandemic is figure out how this generalizes for arbitrary amplitudes in this example. But yeah, just for tree amplitudes, if you have n particle scattering, and so by trees mean there's no loops inside the diagram. Okay, so they just look like trees. For n particle scattering, it's the n-3 associahedron. Yeah, it's the n-3 dimensional associahedron.
So going to higher orders of associahedron corresponds to going higher orders of perturbation.
Well, it's higher orders in perturbation theory, although it's higher orders in perturbation theory largely by just simply going to more particles. You can also keep the number of particles fixed and have more loops in the diagram. Okay, and that's not the associahedron anymore. But there's a new family, infinite family of polytopes, which generalize that. So that's why there's a sort of a story of a generalized associahedron, if you like. But what you can already see from this example is how incredibly basic everything is. It's not like, you know, there's just some that these are essentially combinatorial objects. And they live in kinematic space. They don't live in space-time. They don't live in Hilbert space. They live directly in the space of the sort of kinematical variables. And that notion generalizes. That notion generalizes for all orders of perturbation theory in this example. This was, as I said, is still a somewhat toy example of a theory of scalars. It has a lot of sort of universal features in common with many other theories, but it's a kind of simplest example we can start with, where you can see some of this kind of combinatorial geometry. Ironically, we only ran into this and understood this much simpler example 5 years after we understood a much fancier one directly for gluons, and that's what the kind of next part of the next sort of 10 minutes was about, to just give you a sense for what those ideas are.
Sorry to keep bugging you, just a quick follow-up. So you said we can't calculate loop diagrams. So does that mean you can't get like the total scattering amplitude from just the associahedron picture? Or? Not just from
this associahedron, but there is some generalization of the associahedron that for any order of perturbation theory, any number of particles, any number of loops, it tells you the shape to draw. Yeah.
I see. Okay. Thank you so much. This talk is great so far.
Yeah, thank you so much, Professor. We'd love to have more questions, but in the interest of time, we're going to have to close now. And I just wanted to thank you again, Professor Arkani-Hamed, for an excellent conversation today. It was really a pleasure to hear about this fascinating research. And it's extremely exciting to think about the future of this work. And for the audience, keep an eye out for an announcement on our fall lineup of speakers to be announced soon. Once more, thank you so much, Professor Arkani-Hamed.
Thanks a lot.
Yeah, thank you so much. Yeah.
Thank you.
I hope you all have a good night.
Good night, guys.